There is a number written down in a physics paper, and it is one of the most quietly unsettling numbers ever measured. It is the mass of a particle called the Higgs boson, and it was pinned down at the world's largest atom smasher, the Large Hadron Collider, in the years after 2012. A single number, a measurement, the kind of thing that fills a line in a scientific table and looks like nothing at all. Most people will never hear it, and if they did, it would mean nothing to them. But to the physicists who study how the universe is put together, that number carried a message. And the message was strange and a little frightening, because when you take the measured mass of the Higgs and you feed it into the equations that describe the vacuum of empty space, the equations seem to whisper something that no one quite wanted to hear. Let me tell you a little more about that number, the mass of the Higgs. Because the story of how we got it is one of the great human achievements, and it makes the unsettling message it carries feel more real. For decades, physicists had a theory that predicted a particle, the Higgs boson, tied to the field that gives other particles their mass. But predicting a particle and finding one are very different things. To find the Higgs, they had to build the largest and most complex machine human beings have ever made, the Large Hadron Collider, a ring 17 miles around, buried underground beneath the border of France and Switzerland, cooled to colder than deep space, accelerating particles to almost the speed of light and smashing them together hundreds of millions of times a second. Thousands of scientists from dozens of countries working for decades. And in the summer of 2012 they announced it. They had found the Higgs, the last missing piece of the theory, confirmed at last. It was a triumph, and it was celebrated as one. But once they had the particle, they could measure its mass precisely, and that is where the strangeness crept in. The mass came out to a particular value, and that value, it turned out, sat in a very telling place. Physicists had long understood that the mass of the Higgs, combined with the mass of the heaviest known particle, the top quark, would determine the shape of the landscape the Higgs field lives in, the landscape of valleys and ridges we have been talking about. And when they plugged in the real, measured numbers, the landscape they got was the unsettling one, not clearly stable, not clearly doomed, balanced, right on the edge, in the metastable zone. Here is what I find quietly remarkable about that. We did not set out to discover that the universe might be balanced on a knife's edge. We set out to find a particle, to complete a beautiful theory, to understand how things get their mass. We built the greatest machine in history to do it, and the particle, once found, turned out to carry this second, unasked-for message, almost as a whisper, hidden in the precise value of its mass. The universe, in handing us the Higgs, also seemed to hand us a strange note about its own stability, one we're still trying to read. And this is why physicists take the question seriously, rather than dismissing it as idle speculation. It is not a fantasy pulled from nowhere. It comes directly from our best, most carefully measured understanding of how the universe is built, from a number wrung out of the largest experiment ever performed. The possibility that our vacuum is false is not a story someone made up to frighten people. It is a reading, perhaps not the final reading, but a serious one, of what the real numbers seem to be telling us. That is what makes it worth sitting with, carefully, and worth walking all the way through, to the calm on the other side. They seem to say that empty space, the vacuum, the nothing that fills the universe, may not be truly stable, that it may be sitting, right now, in a state that only looks final, that it could, in principle, fall to a deeper, truer state at any moment. And if it ever did, everything would end. Tonight, we're going to sit with that possibility. The possibility that the universe, the whole thing, is balanced on a kind of edge we cannot see. And the stranger, darker version of the idea, the one that gives tonight its title, the possibility that the falling has already begun, that somewhere out there, perhaps very far away, perhaps long ago, the end has already started, and is on its way toward us right now, and we simply cannot see it coming. I want to be honest with you from the very start, because this is the kind of idea that can be told carelessly, in a way that frightens for no reason. So let me say it plainly. This is a possibility, not a prediction. Nobody is telling you the universe is about to end tonight. The physics here is real, and the question is genuine, and serious people study it seriously. But the most likely answer, as we will see by the end, is gentle. And the timescales involved are so vast that they fold back around into something that feels almost like reassurance. We're going to walk all the way through the frightening part and then all the way out the other side into the quiet. So there is no need to brace yourself. This is not a journey toward fear. It is a journey through it and out. Here is what I hope you will understand by the time we're done. You will understand what it actually means for empty space to be unstable, which is one of the strangest ideas in all of physics. You will understand why, if the end ever came, it would arrive with no warning at all, faster than any alarm could sound. You will understand why some physicists genuinely wonder whether it might have already begun somewhere in the vast universe. And you will understand, finally, why none of this is worth losing a single night's sleep over, why the very same physics that opens the frightening door also, very gently, closes it again. So settle in, get comfortable. There is nothing here that can hurt you. And there is a strange kind of peace waiting at the end of this particular thought, if you're willing to walk through the dark to reach it. And before we go any further, if you find that these slow walks through the strangest ideas in science are the kind of thing that quiets your mind at the end of the day, the kind of thought you would rather sit with at 3 a.m. than be sold something, then take a moment to subscribe or to follow on Spotify. It genuinely helps these quiet journeys reach a few more people who think the way you do. That is all. Now let us begin with the most stable thing you can imagine. And the unsettling idea that even it might be a kind of lie. Look around the room you are in. Feel how settled it is. The air, the stillness, the empty space between you and the walls. Nothing is more ordinary than empty space. It is the very definition of nothing happening, of rest, of stability. If you wanted to point at the most stable, most final, most settled thing in all of existence, you might point at empty space itself, the calm vacuum that fills the universe between the stars. Surely that at least is solid ground. Surely the nothing is permanent. But here is the strange thing physics has come to suspect. Empty space might not be the bottom. It might not be the final resting place it appears to be. It might be more like a ledge, partway down a cliff, a place that looks flat and stable and safe. But that has somewhere below it, a deeper place it could still fall to, and the whole universe might be standing on that ledge, has been standing on it for nearly 14 billion years, perfectly fine, perfectly calm, with no way to know how far the drop below really goes, or whether anything could ever nudge it over the edge. To understand what that means, that empty space might have somewhere lower to fall, we need a picture. Bendustor. And the picture physicists use is simple enough that you can hold it in your mind as you drift. Imagine a ball resting in a valley. It sits at the bottom of a dip in the landscape, settled, going nowhere. Give it a small push and it rolls back down to the bottom. It is stable. That is what we usually mean by stable, a thing that returns to where it was when you nudge it. Now imagine that this valley, the one the ball is resting in, is not actually the lowest point in the whole landscape. Imagine that just over the next ridge, there is a deeper valley, lower than the one the ball is in. The ball cannot see it. The ball is perfectly content where it is. As far as the ball is concerned, it is at the bottom of the world. But it is not. There is a deeper bottom beyond the ridge. And if the ball could somehow get over that ridge, it would roll down into the deeper valley and settle there instead, lower than before. Physicists call the ball's cozy little valley a false vacuum. False, because it looks like the bottom but is not. And they call the deeper valley beyond the ridge the true vacuum, the real bottom, the lowest energy state there actually is. And here is the unsettling idea at the heart of tonight. The vacuum of our universe, the empty space all around us, might be a false vacuum. It might be the ball, resting comfortably in a valley that only looks like the bottom, while somewhere, in the strange landscape of physics, there is a deeper valley it has not found, a truer, lower state of empty space that it could, in principle, fall into. Why would anyone think this? It comes back to that number, the mass of the Higgs boson, and to the particular way the Higgs field fills all of space. The Higgs is not just a particle, it is connected to a field, an invisible presence that exists everywhere, in every cubic inch of the universe. And the value of that field is part of what defines the vacuum, part of what empty space actually is. And when physicists take the measured properties of the Higgs, its mass, and combine it with the mass of another particle, the top quark, and work out the shape of the landscape that the Higgs field sits in, they find something that makes them uneasy. The shape suggests that our vacuum is probably not at the true bottom. It seems to be sitting in a valley stable for now. But with a deeper valley somewhere beyond, a lower state it has not fallen to. Our empty space, by this reading, is very possibly a false vacuum. There is something we have been taking for granted this whole time, and it is worth stopping on. Because once you really understand it, the whole idea of a decaying vacuum makes a deeper kind of sense. We have been talking about empty space as if it were nothing. It is not nothing. Empty space is a surprisingly busy, surprisingly substantial thing. And that is exactly why it can have states and valleys and the capacity to fall. Strip a region of space of everything. Take out every particle of matter, every speck of dust, every atom, every photon of light. What is left, you would think, is pure nothing, a true void. But modern physics says otherwise. What is left is still filled, everywhere, by fields. A field is a kind of presence that exists at every point in space, with a value at every point, even when there are no particles around. The Higgs field is one of these. The fields that carry the forces are others. Even in the emptiest possible region, these fields are there, humming, present, never absent. Empty space is not the absence of everything. It is the quietest possible state of fields that can never truly go away. And those fields are not perfectly still, even in the emptiest void. Quantum physics says they flicker, constantly, with a kind of irreducible restlessness. Tiny fluctuations bubbling up and vanishing everywhere, all the time, even in perfect emptiness. Particles flicker into being and out again, borrowed briefly from the void and returned. Empty space, looked at closely enough, is not a calm nothing but a seething, humming, restless something, a froth of activity that never stops. This is not speculation. We can measure its effects. The restless energy of the vacuum nudges the behavior of atoms in ways we have detected with exquisite precision. The nothing is doing things, measurable things, all the time. So when physicists say the vacuum might decay, they are not saying that nothing might suddenly become something. They are saying that this rich, humming, field-filled state we call empty space might settle into a different, deeper configuration of those same fields. The vacuum has structure. It has a value, set by the fields that fill it, especially the Higgs field. And a thing with structure, a thing with a value, can have a lower configuration it might settle into. That is what the false vacuum idea really means. It is not about nothing falling into something. It is about the fields that fill all of space shifting from one quiet state to a deeper quiet state. And everything built on top of those fields, which is everything changing with them. I find that this reframes the whole subject in a way that makes it less frightening and more wondrous. Empty space is not a fragile nothing that might shatter. It is a deep and structured something, a calm arrangement of the most fundamental fields there are, that has held its configuration steadily for 14 billion years. The vacuum being able to decay is not a sign of fragility. It is a sign of how rich and real empty space actually is, rich enough to have states, deep enough to have a true bottom somewhere, structured enough to be the foundation that everything else is built upon. You are not floating over an abyss of nothing. You are resting on a deep, humming, field-filled foundation that has been steady since the beginning of time, and shows every sign of staying that way for an almost endless age to come. Here is something worth knowing, because it is the reason we cannot simply settle this question once and for all. And it is oddly comforting. The whole frightening conclusion that our vacuum sits in the metastable zone hangs on the precise values of just a couple of numbers. And one of those numbers we do not actually know as well as we would like. The mass of the Higgs we have measured beautifully. But the calculation of vacuum stability is exquisitely sensitive to a second number, the mass of the top quark, the heaviest of all the known particles, and the top quark is a slippery thing to weigh. It is so heavy and so short-lived that it never exists on its own for more than the briefest instant before decaying. And measuring its mass precisely is genuinely difficult, tangled up with subtle questions about exactly what we mean by its mass in the first place. The result is that our knowledge of the top quark's mass carries more uncertainty than we would like, and that uncertainty feeds directly into the stability calculation. And here is why that matters. The boundary between a stable vacuum and a metastable one runs right through the region where our measurements place us. And exactly which side of the line we fall on depends sensitively on that top quark mass. Nudge the value a little one way, and the calculation says the vacuum is metastable, able in principle to decay. Nudge it a little the other way, and the calculation says the vacuum is simply stable, the bull truly at the bottom, no deeper valley anywhere, nothing to discuss. We are so close to the boundary that the uncertainty in a single hard-to-measure number is enough to flip the answer. So the honest state of the science is not that we know our vacuum is false, it is that, with our current best numbers, the most likely reading places us just barely on the metastable side. But only just, and within the uncertainty, perfect stability is entirely possible. We are not standing clearly on a ledge. We are standing somewhere in a fog right around where the ledge might be, unable to tell, with the numbers we have, whether there is any drop there at all. The frightening conclusion is provisional, balanced on a measurement that could still tip either way. I find that genuinely reassuring, and not just because it leaves room for the safe answer. It is reassuring because it reminds us how tentative this all is, how far from a settled verdict. This is not the universe handing us a sentence. It is the universe handing us a hard question, with the answer still blurry, still moving as our measurements sharpen. Over the coming years, as we measure the top quark more precisely, the fog will clear a little. And we will learn which side of the line we're really on. And there is a real chance, a serious chance, that the answer will turn out to be the gentlest one of all, that there was never any ledge, that the bull was at the bottom all along, that the frightening door, when we finally see it clearly, was only ever a shadow on a wall that has no door in it at all. I want to be careful here, because this is exactly the kind of thing that gets overstated. The measurements are not perfect, and the calculation sits very close to a boundary. Depending on the precise values, the universe could be in one of three situations. It could be truly stable, the bull really at the bottom, nothing to worry about ever. It could be unstable, genuinely able to fall, though perhaps not for an enormously long time. Or it could be right on the knife's edge between the two, a situation physicists call metastable, which means stable for now, stable for a very, very long time, but not stable forever, not truly at the bottom. And the strange, striking thing about our universe is that the measurements place us almost exactly on that knife's edge, not comfortably stable, not clearly doomed, right on the line between them, in the metastable zone, balanced. The idea of a decaying vacuum did not arrive with the Higgs. It is older than that, and it has a particular father, a physicist whose name deserves to be remembered when this subject comes up. Because he worked out the strange mathematics of it long before anyone could measure whether it applied to our universe. His name was Sidney Coleman, and he was one of the most brilliant and beloved theoretical physicists of the 20th century, known for a mind so sharp and a wit so dry that his lectures became legendary. In the 1970s, working in part with a colleague, he turned that mind toward a strange question. What would happen, mathematically, if the vacuum of space were not truly stable? How would a false vacuum actually decay? And in a series of papers, he worked out the answer with beautiful precision, laying down the framework that physicists still use today. Coleman showed that a false vacuum would not decay all at once, everywhere. It would decay the way we have described, through the formation of bubbles, little pockets of true vacuum appearing here and there by quantum chance, each one with a wall separating the new reality inside from the old reality outside. He worked out how likely such a bubble was to form, how big it had to be to survive and grow rather than collapse back, and how its wall would race outward once it did. There is even a paper he wrote, with a colleague, with a wonderfully understated title about the gravitational effects of vacuum decay, in which they extended the whole frightening picture to include gravity, the full machinery of how a universe might unmake itself. He was describing the end of everything, and he did it with the calm precision of a man solving an interesting puzzle. There is a famous line, often associated with this work, that captures the strange spirit of it. The decay of the false vacuum, Coleman and his colleague wrote, would be the ultimate ecological catastrophe, because the new vacuum would be incompatible with any of the structures, any of the chemistry, any of the kinds of matter that make up the world we know. And yet, they noted, with the dark humour that ran through Coleman's work, one can at least take comfort in the thought that the new vacuum would surely permit, eventually, new and interesting structures of its own, even if not us. It is a remarkable thing to describe the total end of your own kind of reality and find in the same breath a wry kind of consolation in it. I bring Coleman up not to frighten you further, but for the opposite reason. This idea has been studied carefully, rigorously, by some of the finest minds in physics for half a century. It is not a wild rumour. It is a well-understood piece of theoretical physics, its mathematics worked out in detail, its consequences traced with care, and that careful study is exactly what gives us the reassurance we will keep returning to. We understand this possibility well enough to know not only that it exists, but how unlikely it is, how vast the timescales are, how patient the false vacuum, if that is what we are, has proven to be. Coleman opened the door and described what was behind it, and the same careful work that described the danger is what lets us close the door again, gently, and rest. That in itself is one of the genuine mysteries of modern physics. Why should our universe sit so precisely on the boundary between stability and collapse? Nobody knows. It might be a coincidence. It might be telling us something deep that we do not yet understand. But there it is, in the numbers. We appear to live in a universe that is balanced, almost perfectly, on the edge between a vacuum that is safe forever and a vacuum that could, someday, fall. There are a few misunderstandings about all of this that float around, and clearing them away makes the whole picture calmer and clearer, so let us take a moment for them. The first misunderstanding is that this is a prediction, that physicists are warning us the universe is about to end. It is nothing of the kind. It is a possibility, one reading of uncertain measurements, studied as a way of understanding the deep structure of reality. No serious physicist is forecasting vacuum decay anytime soon, or assigning it any meaningful chance within any human, or stellar, or even galactic timescale. When you see a dramatic headline suggesting the universe could end at any second, the honest translation is much gentler. It means there is an interesting open question about whether our vacuum is perfectly stable. And the most likely answer, even in the worrying case, involves timescales so vast they are beyond meaning. The drama is in the telling, not in the physics. The second misunderstanding is that something we do could trigger it. People sometimes worry that a powerful enough experiment, a big enough particle collider, might accidentally nudge the vacuum over the edge. This worry, while understandable, does not survive a moment's thought about cosmic rays, which we will keep coming back to because it is so reassuring. Nature has been colliding particles at energies vastly beyond anything our machines can reach, constantly, everywhere, for 14 billion years. If such collisions could trigger vacuum decay, it would have happened long ago, somewhere close enough to have reached us. It has not. Nothing we could build comes remotely close to the energies nature throws around for free, and nature has never once tripped the switch. Our experiments are, by this measure, utterly harmless. The third misunderstanding is that if it is possible, it is somehow likely that being on a knife's edge means we are in danger. But possible and likely are very different things, and the gap between them here is almost beyond imagining. The vacuum being metastable does not mean it is teetering, ready to fall at the slightest disturbance. It means there is, in principle, a deeper state it could eventually reach, with the waiting time for that to happen stretching past the death of the last star. A thing can be possible and still be, for every practical purpose, never going to happen. That is exactly the situation here. The knife's edge is real, but the universe has been balanced on it, perfectly steady, for its entire existence, and shows every sign of staying balanced for an almost endless time to come. The fourth misunderstanding is that the whole idea is settled, that we know our vacuum is false. We do not. The measurements that place us in the metastable zone are close to the boundary, and they carry real uncertainty. It is entirely possible that as our measurements of the Higgs and the top quark grow more precise, the picture will shift. And we will find that our vacuum is simply stable after all, the ball truly at the bottom, no deeper valley anywhere. The metastable reading is the current best guess, balanced right on the line. But it is a guess that could tip either way as the numbers sharpen. We may yet learn that the frightening door was never really there at all. So hold the whole thing lightly. It is a real and fascinating question about the deepest nature of empty space. It is not a warning, not a danger we can trigger, not a likelihood, and not even a settled fact. It is a strange and beautiful uncertainty at the edge of our knowledge, the kind of thing worth thinking about in the dark precisely because it asks nothing of you, threatens nothing you love, and leaves you, when you have turned it over, exactly as safe as you were before. And perhaps a little more amazed at the universe you get to be safe in. And the question that follows is the one that makes your skin prickle a little, in the dark. If our vacuum is sitting in a false valley, with a deeper one somewhere beyond the ridge, what would it take to push it over? What could possibly send the entire universe rolling down into a deeper state? And what would happen to everything? To the stars? To the Earth? To us? If it ever did. Here is where most people, when they think about the end of the universe, imagine one of two doors. Behind the first door is a slow ending. The universe keeps expanding. The stars slowly burn out one by one over trillions of years, and everything gradually cools and dims and fades into a cold, dark, empty silence. A whimper, not a bang. The long, gentle heat death of the cosmos. So slow that it is almost peaceful, an ending measured in numbers so large they stop meaning anything. Most people who know how the universe is likely to end picture something like this, a slow fade to black. Behind the second door is a collapse. The expansion of the universe somehow reverses, and everything that flew apart begins to fall back together, galaxies rushing toward galaxies, the whole cosmos contracting faster and faster, until it all slams back into a single point, a great crunch, the Big Bang run in reverse. This one is more dramatic, more violent. But it is still, in its way, a familiar kind of ending, a collapse, a falling together, the universe folding back up. It is worth placing vacuum decay alongside the other ways the universe might end, because seeing them together puts it in perspective. And most of them, you will notice, are far gentler than the dramatic third door, and all of them are unimaginably far away. The most likely ending by current understanding is the slow one we called the first door, the heat death. The universe keeps expanding, and that expansion appears to be speeding up, driven by the mysterious dark energy that fills space. Over trillions of years the stars burn out, no new ones form, the galaxies drift apart and fade. And everything cools toward a uniform, dark, near-frozen stillness. It is not violent. It is not sudden. It is the universe simply running down, like a fire settling into embers and then into cold ash, over spans of time so vast that the word slow does not begin to capture them. This is where most cosmologists would put their money for the actual fate of the cosmos. A long, quiet, fading into the dark. There is a more dramatic variation, sometimes called the Big Rip, in which the dark energy that drives the expansion grows stronger over time rather than staying constant. If that happened, the expansion would eventually become so fierce that it would tear apart not just galaxies but solar systems, then planets, then atoms themselves. The very fabric of space stretching everything to shreds in a final flourish. This one is more violent, but it is also considered less likely on current evidence. And like all of these, it lies an enormous distance in the future, if it comes at all. There is the old idea of the Big Crunch, the second door, in which the expansion reverses and everything falls back together into a final collapse. On current evidence, with the expansion speeding up rather than slowing, this one looks unlikely. The universe seems far more inclined to expand forever than to fall back. But it remains in the catalogue of possibilities, a universe that breathes out and then someday breathes back in. And then there is vacuum decay, the third door, the one we have spent tonight with. Notice how it differs from all the others. The heat death, the Big Rip, the Big Crunch, all of them are slow. All of them unfold over enormous visible stretches of time. All of them give the universe a long traceable decline. Vacuum decay is the only one that could, in principle, happen at any moment, with no warning, no slow build-up, no decline. It is the wild card, the only sudden ending in the catalogue. That is what makes it feel so different and so unsettling. But it is also, by most reckonings, among the least likely to actually be the way things go. And certainly the one whose timescale, if it happens at all, stretches furthest into the unimaginable future, past even the heat death. So in the full catalogue of cosmic endings, vacuum decay is the strange outlier, the dramatic possibility, the one that makes for the most unsettling thought. But it sits among gentler, more probable, more familiar endings, all of them so distant that they have nothing to do with any living thing. The universe will very likely end, if end is even the right word, with the quiet fade of the heat death, ages upon ages from now, the stars going out one by one into a long and peaceful dark. That is the honest, most likely picture. The third door is real and fascinating and worth knowing about. But it is not the door the universe is most likely to walk through, and whichever door it is, it lies so far ahead that the entire bright history of the cosmos, including all of us, is just the opening moment of a story whose ending is unimaginably far from being told. These are the two doors people argue about: the slow fade or the great collapse, the whimper or the crunch, and both of them, you will notice, are far away. Both of them take almost unimaginable stretches of time. Whichever one is real, it is trillions upon trillions of years away. So distant that it has nothing to do with us, nothing to do with tonight, nothing to do with any living thing that will ever exist on Earth. Both of these endings are safe in a sense, precisely because they are so impossibly far off. But there is a third door, And the thing about the third door is that it does not come with a timeline. It does not promise you trillions of years of warning. It is the possibility we have been circling, the false vacuum, the ledge that the universe is standing on. And if that is what we are, a false vacuum, then the end does not have to be slow. And it does not have to be far away. It could happen at any moment. It could be happening right now. And if it is, you would have no way of knowing, no warning, no sign, nothing until it arrived. And by the time it arrived, there would be no you left to notice. Let me tell you how the third door works, because it is genuinely one of the strangest ideas in all of physics. And once you see it, you cannot unsee it. If our vacuum is a false vacuum, sitting in its valley with a deeper valley beyond the ridge, then it does not actually need anything to push it over the ridge. This is the part that surprises people. In the strange world of quantum physics, things do not always have to climb over barriers. Sometimes they can simply appear on the other side, through an effect called quantum tunneling. A quantum system sitting in a false valley has a tiny chance at any given moment of simply tunneling through the ridge without ever going over it, and finding itself in the deeper valley beyond. It does not need a push. It does not need a trigger. It can just happen spontaneously by pure quantum chance, anywhere, anytime. We have leaned on this idea of quantum tunneling, the notion that a thing can pass through a barrier it does not have the energy to climb over, and it is strange enough that it is worth slowing down on, because it is one of the genuinely real and genuinely bizarre features of the world at its smallest scale. In the everyday world, if you want to get a ball over a hill, you have to give it enough energy to reach the top. If it does not have enough, it rolls partway up and comes back down. It cannot get to the other side. That is just how the world works, at the scale of balls and hills and human beings. But the quantum world, the world of particles and fields, does not obey that rule. Down there, a particle sitting on one side of a barrier has a small but real chance of simply appearing on the other side without ever having had the energy to climb over. It does not go over the barrier. It goes through it, in a sense, by a kind of probabilistic borrowing that the universe permits at the smallest scales. This is quantum tunneling, and it is not a theory waiting to be confirmed. It is real, observed, relied upon. In fact, you depend on it. The sun shines because of quantum tunneling. Deep in the sun's core, the particles trying to fuse together do not actually have enough energy to overcome the force pushing them apart. By the rules of the everyday world, the sun should barely shine at all, but quantum tunneling lets the particles pass through that barrier anyway, a small chance each time multiplied by an unimaginable number of particles. And so the sun burns. The light that warms your face on a clear day, the light that grew the food you eat, all of it flows from this strange quantum permission to pass through walls. Tunneling is not exotic. It is woven into the most basic workings of the universe and into your own existence. So when physicists say that a false vacuum could decay by tunneling, they are not invoking some speculative new magic. They are applying the same well-understood, experimentally confirmed effect that powers the sun, only on the grandest possible scale, to the vacuum itself. The vacuum, sitting in its false valley, has, by the rules of quantum mechanics, a tiny chance at any moment of tunneling through the ridge to the deeper valley beyond. It does not need a push. It does not need energy. It can simply, by quantum chance, find itself on the other side, the way a particle in the sun finds itself fused. That is what makes the third door so strange. It does not require any trigger at all. It is built into the deepest rules of reality, the same rules that, in their gentler moments, light the stars. But here is the reassuring flip side, and it is the same logic that lights the sun, turned around. Tunneling is rare. For any single particle in the sun, in any given moment, the chance of tunneling is minuscule. It only adds up to something because there are so many particles and so much time. And for the vacuum, the barrier is so wide, the ridge so high, that the chance of tunneling through is smaller still, smaller almost beyond comprehension. The very effect that makes vacuum decay possible also, by its nature, makes it staggeringly unlikely in any moment that matters. Tunneling is real, but the bigger and wider the barrier, the more patient you have to be. And the barrier around our vacuum is so vast that the waiting time stretches past the lifetime of the stars. And when it happens, it does not happen everywhere at once. It happens at a single point. Somewhere in the vast universe, in one tiny region, the vacuum tunnels through to the true deeper state. A single bubble of true vacuum appears, a little pocket of the deeper reality, surrounded by the old false vacuum we still live in. And that bubble, the moment it appears, begins to grow. The true vacuum is lower, deeper, more stable, and so the boundary between it and the old false vacuum sweeps outward, the bubble expanding, the region of true vacuum eating into the region of false vacuum, converting everything it touches into the new deeper state. The bubble grows and does not stop. That is the third door. Not a slow fade, not a great collapse, a bubble appearing from nowhere by quantum chance and spreading outward to swallow everything. And the most chilling part, the part we have to look at next, is how fast that bubble moves and what that speed means for any warning we might ever hope to get. There is a much larger picture that this whole idea fits into, and it is one of the strangest and most beautiful in all of cosmology. So let us drift out to it for a while, because it changes how the third door feels. We talked earlier about inflation, the burst of explosive expansion in the first instant of the universe, driven by a high-energy false vacuum that then decayed. Some cosmologists take that idea further, into something called eternal inflation. The thought is this: if inflation is driven by a false vacuum, and false vacua decay by forming bubbles, then perhaps inflation never fully stops everywhere at once. Perhaps in some vast inflating background, bubbles of lower vacuum are constantly forming here and there, each one a region where inflation has ended and a universe has settled out. Each bubble becomes its own pocket cosmos, with its own history, perhaps its own laws, expanding inside an endlessly inflating sea. And our entire universe, everything we can see, all 14 billion years and all the billions of galaxies of it, would be the inside of one such bubble, one pocket among countless others in a vast and possibly endless multiverse of bubbles, if that is true, and it is speculative. But it follows naturally from ideas we have good reason to take seriously, then it casts the whole question of vacuum decay in a new light. Our universe would itself be the product of a vacuum decay, one bubble that formed when a higher vacuum fell, and the deeper valley we have been worried about falling into would simply be another step in the same endless process, our bubble someday giving rise to a deeper bubble, the way the inflating sea gave rise to ours. Vacuum decay, in this picture, is not a freak catastrophe lurking at the end of things. It is the basic creative engine of the multiverse, the process by which universes are born from one another, endlessly, each falling vacuum spawning new pockets of reality. And there is something oddly consoling in that grand view. If our universe is one bubble among countless others, then even the most complete vacuum decay, even our entire cosmos giving way to a deeper state, would not be the end of everything. It would be one bubble among many, transforming, while elsewhere in the endless sea new bubbles keep forming, new universes keep being born, the great process rolling on without us. The multiverse, if it is real, does not end when one bubble falls, it simply keeps making more. Our ending, even the total kind, would be local, a single pocket turning over, in a reality far too vast for any single ending to touch. I want to be clear that this is the speculative frontier, not established fact. We cannot see other bubbles, we cannot test eternal inflation directly, at least not yet. It is a possibility, a place where our best ideas seem to lead, not a thing we know. But it is worth holding alongside the fear, because it reframes the whole subject. the falling of a vacuum stops looking like pure destruction and starts looking like part of an endless cycle of cosmic birth, the same process that may have made us, rolling on to make others world after world after world in a sea of inflation without end. So if you like, you can let the third door open onto this instead, not a wall of annihilation racing through the dark, but a single bubble among endless bubbles, our pocket of reality eventually turning over somewhere unimaginably far in the future, while the great sea goes on giving birth to universes, including, perhaps, ones where beings like us will someday lie awake in their own quiet rooms, wondering the very same wondering, safe in their own long stability, children of the same endless falling that made us all. There's a remarkable twist to this whole story, and it is one of my favourite ideas in all of cosmology, because it suggests that a vacuum decay, far from being only an ending, may have been the very thing that gave us our beginning. Cast your mind back to the first instance of the universe, the moment just after the Big Bang. Cosmologists have strong reasons to believe that in those first unimaginably brief moments, the universe underwent a burst of expansion so violent and so sudden that it almost defies description, doubling in size again and again in a sliver of a second, growing from smaller than a single particle to enormous in less time than it takes to think the word. They call this inflation. And the evidence for it is written across the sky in the faint patterns of the afterglow of the Big Bang. Inflation is one of the cornerstones of modern cosmology, and what drove that sudden, explosive expansion. The leading idea is that the early universe was sitting in a kind of false vacuum of its own, a high-energy state, a valley that was not the bottom. While it sat there, that high-energy vacuum drove the runaway expansion of inflation, and then the false vacuum of the early universe decayed. It fell to a lower state, ending inflation, and in the process dumping its enormous energy into the creation of all the matter and radiation that would become everything, every particle, every star, every galaxy, every atom in your body. The end of one false vacuum in this picture was the beginning of the universe as we know it. A vacuum decay did not destroy a world, it made one. Sit with the symmetry of that for a moment, because it is genuinely beautiful. The same kind of process that we have been fearing tonight, a false vacuum falling to a lower state, may be the very thing that lit the universe into being. At the beginning, a vacuum decayed, and from that decay poured all the matter and energy that became us. And at the end, if our own vacuum is false, another such decay might one day sweep it all away again. The same mechanism, bookending all of cosmic history, a vacuum decay at the dawn that creates, and perhaps a vacuum decay in the unimaginably distant future that transforms, creation and ending, the same kind of event, the universe born from one falling and perhaps someday remade by another. This reframes the third door entirely, I think. It is not simply a door marked end. It is a door marked change, the same door the universe came through at its birth. The falling of a false vacuum is not unique to destruction. It is one of the deepest creative processes the cosmos has, the engine that may have built everything we see. When you picture the bubble of true vacuum, do not only picture it sweeping things away. Remember that a very similar event near the beginning of time swept a featureless high-energy state into the rich, structured, star-filled universe we live in. The vacuum falling is not only how things might end, it may be how everything began. And so even the most frightening idea in tonight's journey turns out to have, woven into it, the story of our own origin. We may be the children of a vacuum decay, here because long ago, a false vacuum fell and poured out the makings of a universe. There is no need to fear a process that may have given us everything. There is only perhaps a kind of awe at the deep unity of it, the same gentle falling at the root of both the beginning and the end, the universe turning over once to make us. And perhaps, almost infinitely far from now, turning over once more. The bubble of true vacuum, once it appears, expands outward at very nearly the speed of light. Sit with that for a moment, because it is the key to everything frightening about this idea. And also, strangely, to everything reassuring about it. The wall of the bubble, the boundary where the old reality turns into the new, races outward at almost the fastest speed anything can go, the speed of light itself, the speed of the very signal that would have to reach you to warn you. And that is why there could be no warning. Think about how you ever come to know that anything is happening far away. You see it, which means light from it reaches your eyes. You hear about it, which means a signal, a radio wave, a message travels to you. Every possible warning, every possible sign that something is coming has to travel to you somehow, and nothing can travel faster than light. But the bubble wall is moving at the speed of light, so the bubble arrives at the exact same moment as any light that could have warned you about it. There is no gap. There is no advance notice. The information that the end is coming travels at the same speed as the end itself. The two arrive together, or rather, the end arrives, and the warning never does. Because the warning and the end are the same wavefront, racing toward you side by side. So if a bubble of true vacuum was sweeping toward the Earth right now, from somewhere out in the galaxy, you would see absolutely nothing. The sky would look normal. The stars would shine as they always have. Everything would be perfectly calm, right up until the instant the bubble wall arrived. And then, in less time than any nerve in your body could carry a signal, less time than a single thought, everything would change. There would be no pain, no fear, no awareness of it at all, because awareness itself takes time, and there would be no time. You would simply, in the most literal sense imaginable, cease, along with the earth, the sun, and everything else the bubble touched, all of it converted in an instant to the new state of the vacuum. I know how that sounds. I told you we were going to walk through the frightening part, and this is the heart of it. But stay with me, because there is something almost merciful hidden inside this very fact, and it is worth seeing clearly. An ending with no warning is also an ending with no dread. There would be no moment of seeing it coming, no terror, no suffering, no goodbye. Whatever else this would be, it would be utterly painless and utterly instantaneous, the gentlest possible version of an ending, in the sense that no one would ever experience it as an ending at all. One moment everything is exactly as it is now, the next moment nothing, and no one left to notice the nothing. If you must imagine the universe ending, this is, in a strange way, the kindest form it could take. No fear, no pain, no warning. Just the quiet you already have, made permanent. A natural question, and maybe one that has been quietly nagging at you, is whether we could ever detect a bubble coming. If one were out there, expanding toward us, is there truly no way to see it? No early warning system, no telescope that could catch it on approach? It is worth answering this carefully, because the answer is part of what makes the idea so strange. And yet the answer also dissolves into reassurance. The short answer is no. We could not see it coming, and we have already touched on why. The bubble wall moves at essentially the speed of light, and so does any light or signal that could carry word of it. There is no possibility of advance warning, because warning requires a signal that outruns the thing it is warning about, and nothing outruns light. A bubble approaching at light speed arrives at the same instant as the first possible glimpse of it. So in the most literal sense, there is no telescope, no detector, no system, even in principle, that could ever spot an incoming bubble in time for that knowledge to mean anything. The information and the event are the same wavefront. But sit with what that actually implies, because it is not as grim as it first sounds. It means there is nothing to watch for, and therefore nothing to dread. A danger you could see coming, would invite a lifetime of scanning the sky, of anxiety, of waiting. This is the opposite. It is, by its very nature, completely outside the realm of anything you could ever observe, prepare for, or worry about productively. There is no vigil to keep because no vigil is possible. The one ending that gives no warning is also the one ending you are completely freed from watching for. You could spend your whole life staring at the sky and you would never see it, which means you are perfectly entitled never to look. And there is a deeper reassurance folded inside this, one we have already met, because the bubble cannot be seen until it arrives. And because we are still here, sky intact, stars shining, we know that no bubble has arrived. And given the speed of light and the vast time the universe has existed, the simple fact of our undisturbed existence already rules out any bubble having formed within an enormous region around us, throughout an enormous span of the past. If a bubble had formed anywhere near us, in cosmic terms, at any point in the deep past, it would already have swept over us. It has not. So while we cannot see a bubble coming in the future, our very survival tells us that no bubble has been coming, through all the vast reach of space and time that could already have reached us. The silence we cannot pierce is also a silence that so far has held completely. So the inability to detect a bubble is not really a source of dread, it is a release from one. There is no instrument to build, no sky to scan, no early sign to fear missing. The whole category of the worry is simply closed off, removed from the realm of things you can do anything about, and therefore removed from the realm of things worth carrying. You are free of it completely, not because the danger is disproven, but because it is, by its very nature, utterly beyond the reach of your attention. And the only news your attention can actually gather, the calm sky, the steady stars, the ordinary night, is good news, the same good news the universe has been quietly delivering every single night for 14 billion years. And here is where the title of tonight comes back, and where the idea turns from frightening to genuinely vertiginous. Because if the bubble moves at the speed of light and gives no warning, then how do you know it has not already started? Somewhere out in the universe, in the billions of years it has existed, in the unimaginable vastness of space, a bubble of true vacuum could already have formed. It could be out there right now, expanding, sweeping through space at the speed of light, swallowing star systems, swallowing galaxies, growing for thousands or millions or billions of years already. And we would have no idea. We could not see it. The light that would show it to us is travelling at exactly the same speed as the bubble wall, arriving at the same instant. So as far as we can ever know, the end may have already begun. It may be on its way. It may have been on its way for a very long time, and we would be sitting here in our calm and ordinary night, with the sky looking perfectly normal, completely unaware, until the moment it arrives, which we would never experience as a moment at all. That is the terrifying possibility in the title. Not that the universe will end, but that, in a sense we can never check, it may already have ended somewhere. And the ending is simply still in transit, racing toward us through the dark, hidden inside its own perfect silence. Here is a question that might be drifting through your mind, and it is a strange and fascinating one. What would the inside of the bubble actually be like? What is the true vacuum, the deeper reality that the false vacuum would fall into? The honest answer is that we cannot know in detail, and that is part of what makes it so eerie. The true vacuum is not just our universe with the lights turned off. It is a different state of empty space itself, a different setting for the fundamental fields that everything is made of. And when those fields settle into a different state, the rules that govern matter change. The strengths of the forces might be different. The masses of particles might be different. The delicate balances that allow atoms to exist, that allow protons and neutrons to hold together, that allow chemistry and therefore stars and planets and life, might simply not hold anymore. Inside the bubble, The very scaffolding that makes our kind of matter possible could be gone. This is why the inside of the bubble would not contain a damaged version of our world, but rather no version of our world at all, the atoms that make up the earth and the air. And you depend on the precise values of the constants of nature as they are in our vacuum. Change those values even a little, and atoms as we know them might not be able to form. The new vacuum would not be a place where things are broken. It would be a place where the rules that allow our kind of thing to exist were never written. Whatever the bubble swept over would not be destroyed so much as rewritten, replaced by a region operating on different fundamental terms under which nothing familiar could survive. And yet, remember that wry note from Coleman and his colleague. The new vacuum, whatever it is, would be a stable, settled state of its own, a true bottom of the landscape, and over the vast stretches of time that would follow, it is at least conceivable that the new vacuum could permit its own kinds of structure, its own forms of complexity, its own strange order built on its own different rules. Not us, nothing we would recognize, but perhaps not nothing either. The bubble would not be an expanding sphere of pure annihilation exactly. It would be an expanding sphere of difference, of other rules, of a reality unlike ours, which might, in its own unimaginable way, eventually become a setting for things we cannot picture. There is something almost beautiful in that thought, if you let the fear settle. The end that the third door represents is not necessarily the end of everything forever. It might be the replacement of one kind of universe with another, our familiar reality giving way to a deeper, stranger one, the way one landscape gives way to another beyond a ridge. We would be gone, and everything we know would be gone. But the universe itself, in some form, on some new terms, might simply continue. The bubble is an ending only from the inside of our particular valley. From the outside, from the longest possible view, it might be less an ending than a turning of the page into a chapter written in a language we will never read. But I want to keep this in proportion, because we are speaking of something almost certainly so far off that the stars will die first. This is the thought experiment about the deep nature of reality, not a forecast. The inside of the bubble is a place we will never see, never reach, never be touched by, on any time scale that could ever matter to a living thing. It is worth wondering about, the way it is worth wondering about anything vast and strange and beautiful. And then it is worth setting gently aside, and returning to the calm, ordinary, perfectly stable night that is the only reality you will ever actually live in. Now let us walk out the other side, because I promised you that the same physics that opens this frightening door also, very gently, closes it again, and that is true. And it is where we are going to spend the rest of our time tonight, in the reassurance, which is just as real as the fear, and far more likely to matter. Start with the simplest reassuring fact, and it is a big one. The universe has been here for nearly 14 billion years. 14 billion years of empty space sitting in its valley, and it has not fallen. If the vacuum were going to decay easily, quickly, often, it would almost certainly have done so already, somewhere close enough to have reached us by now. The fact that we are here at all, that the universe has lasted this long, that the night sky is full of stars and not full of an expanding wall of true vacuum, is itself powerful evidence that whatever the chance of decay is, it is extraordinarily small. We are living proof that the false vacuum, if that is what we are, is a very, very patient one. If the idea of something being metastable, stable, but not truly at the bottom, still feels abstract, here is something that might make it click. And it is sitting, perhaps, on someone's finger nearby. A diamond, that hardest and most permanent seeming of things, the very symbol of forever, is metastable. It is not actually the most stable form of carbon. The most stable form of carbon, the true bottom of the valley for carbon atoms at the surface of the Earth, is humble graphite, the soft grey stuff in a pencil. A diamond, in the deepest thermodynamic sense, would rather be graphite. It is sitting in a false valley of its own, a high state with a lower state, graphite, waiting beyond a ridge. Every diamond in the world is very slowly trying to become pencil lead, and yet diamonds last. They do not crumble into graphite before your eyes. They sit on rings and in vaults, sparkling for human lifetimes, for thousands of years, looking utterly permanent. Why? Because the barrier between diamond and graphite, the ridge between the valleys, is enormous. To rearrange the carbon atoms from the diamond structure to the graphite structure takes a huge push. And at ordinary temperatures, that push essentially never comes. The diamond would have to wait on its own for a span of time so long it dwarfs the age of the universe before it spontaneously turned to graphite. So in practice, it never does. It is metastable, technically able to fall to a lower state. And yet, for every purpose that could ever matter to a person wearing one, completely permanent. This is exactly the situation physicists suspect for our vacuum, and seeing it in a diamond makes it so much less frightening. A diamond is metastable, and no one lies awake worrying that their diamond will suddenly become a smear of pencil graphite. We all happily treat diamonds as forever, because the timescale for them to change is so absurdly long that forever is, for us, the honest word. The vacuum, if it is metastable, is in the very same situation, only more so. The barrier is even higher, the waiting time even longer, the practical permanence even more complete. If you can wear a metastable diamond without a flicker of worry, you can live in a metastable universe the very same way. I love this comparison because it takes something that sounds like cosmic horror, an unstable universe poised to fall, and shows you that you are already, comfortably, surrounded by the very same kind of thing. And you never gave it a second thought. The diamond on the ring, the graphite in the pencil, the false valley and the true one. The high state patiently refusing to fall for longer than the universe has existed. Metastability is not exotic. It is ordinary. It is jewelry. It is the quiet, reliable not falling of things that could in principle fall, but effectively never will. So the next time the phrase false vacuum sends a small chill through you, picture a diamond. Picture how permanent it looks, how safely people treat it, how the word forever fits it so naturally, even though, strictly speaking, it is living on borrowed time, slowly yearning toward graphite it will never reach. Our universe may be exactly that kind of forever, not the absolute guaranteed bottom of everything kind, the diamond kind, the kind that is so reliably permanent on every scale that touches a life that the difference does not matter, and you can wear it and rest in it without a moment's fear. And the numbers, when physicists try to estimate them, bear this out in a way that is almost comically reassuring. If our vacuum is metastable, sitting on that knife's edge, then the typical time you would expect to wait before it decays is not millions of years, and not billions, but a number so large it makes the current age of the universe look like nothing at all. We are talking about timescales with hundreds of zeros, numbers so vast that the entire 14 billion year history of the cosmos so far is less than a rounding error within them. The most likely estimates suggest the vacuum, if it decays at all, would decay on a timescale so long that the universe would have grown cold and dark and empty, every star burned out, long, long before the vacuum ever fell. The heat death we talked about behind the first door would very likely arrive first, ages and ages before the third door ever opened. There is a deeper and subtler reassurance hidden in our own existence, and it is the kind of idea that is fun to turn over slowly in the dark, because it bends back on itself in a way that is almost dizzying. Think about what it takes for you to be here, thinking this thought. The universe had to last nearly 14 billion years without the vacuum decaying. The Earth had to form, life had to arise, Evolution had to run its long course, civilization had to develop, and you had to be born and grow up and end up lying here tonight. All of that takes time, an enormous amount of time, almost 14 billion years of it, during which the vacuum had to stay exactly where it is, in its valley, never falling. If the vacuum decayed easily, if bubbles of true vacuum formed often, then this long stretch of stability would never have been available. The universe would have been swept away somewhere, long before complex life had time to emerge and look up and wonder about it. So here is the strange logic. The very fact that anyone exists to ask whether the vacuum is stable is itself evidence that it is extraordinarily stable. We could only ever find ourselves in a universe that had lasted long enough to produce us. Which means we could only ever find ourselves in a universe where the vacuum had held for billions upon billions of years. A universe with an unstable, quickly decaying vacuum would have no one in it to worry about the matter. The question can only be asked in a universe where the answer is reassuring. The asking is itself the proof. Physicists sometimes call this kind of reasoning anthropic, a way of noticing that our own existence filters which universes we could possibly observe. And while it has to be used carefully, here it carries real weight. It means we should not be surprised to find ourselves in a long-lived, stable universe, because no other kind could contain us. And it means that the 14 billion years of stability behind us is not a lucky streak that might end at any moment, but a precondition of our being here to notice it. We are not gamblers who have been winning and might suddenly lose. We are the kind of thing that can only exist after a very long run of stability, looking back at that run, and finding, of course, that it held. There is a quiet comfort in that, deeper than the comfort of the timescales or the cosmic rays. It says that your existence, the fact of your being here at all, is woven from cosmic stability. You're made of the universe's steadiness. Every cell in your body is the end product of billions of years during which empty space stayed exactly where it was, never wavering, holding the stage steady long enough for something like you to appear on it. You're not standing on thin ice that might crack. You're standing on ground so steady that it had time to grow you. The very capacity to fear the end is proof of how long the universe has refused to end. So let that fold the fear back on itself gently. The thought that frightens you, the possibility of an ending, can only occur to a being that is the fruit of an almost endless stability. The fear is a kind of monument to how safe you've always been. You could not be here to feel it otherwise. So the honest picture is this. Yes, our vacuum may be a false vacuum. Yes, in principle, it could decay at any moment, with no warning. But the chance of it happening in any given moment, in any given year, in any billion billion years, is so unfathomably small that it rounds, for every purpose that could ever matter to a living being, to zero. It is not that it cannot happen. It is that the universe would have to wait, on average, almost forever for it to happen. And almost forever is so much longer than anything you will ever experience that it ceases to be a danger and becomes instead just a strange and beautiful fact about the deep nature of reality. Let us try to actually feel the size of the timescale involved, because I keep saying the numbers are unimaginably large. And it is worth pausing to let just how large sink in, since that size is, in the end, the deepest reassurance of all. The universe is about 14 billion years old. That is already a number beyond real intuition. If you tried to count to 14 billion, one number a second, never stopping, it would take you longer than the universe has existed. The whole of human history, every civilization, every life ever lived, fits into the last tiny sliver of those 14 billion years. It is, by any human measure, an eternity. And yet, against the timescales that physicists estimate for vacuum decay, 14 billion years is nothing at all. It is not a millionth, not a billionth, not a trillionth of the way there. It is so close to zero compared to the decay time that it does not register. The estimates for how long a metastable vacuum like ours would take to decay are written as a one followed by hundreds of zeros in years. There is no way to picture such a number directly, so let me try to give you a sense of it by comparison. Consider the slow, far future death of the universe. The heat death we talked about behind the first door. The stars will keep forming for a while yet, then star formation will end. And the last stars will slowly burn out over trillions of years. Then, over vastly longer spans, even the dead remnants will fade, the galaxies will scatter, and matter itself may eventually decay away. This long fading, the full heat death of the cosmos, plays out over timescales that already dwarf the present age of the universe, almost beyond comprehension. And the vacuum decay timescale is longer still. Longer than the life of the stars, longer than the slow fade of everything. The vacuum, if it falls at all, would very likely fall only after the universe had already grown cold and dark and empty. The light's all gone out, ages and ages before. So picture the order of events on the longest possible view. First, the long, bright era of stars, which we are in now, lasting trillions of years. Then the slow fade, the stars dying, the galaxies dimming, the universe cooling toward darkness, over timescales that make the bright era look brief. And only then, far beyond even that, in a cold and empty cosmos where everything familiar is long gone, might the vacuum finally perhaps fall. The frightening door is not just far off, it is the very last door, the one at the end of the longest hallway imaginable, far past the death of the stars, far past anything that could ever resemble the universe we know. This is why the danger, real as it is in principle, simply cannot touch us. Not us as individuals, not humanity, not life on Earth, not the Earth itself, not the sun, not the galaxy, not the stars, not even the bright star-filled era of the universe as a whole. All of that, every bit of it, will have come and gone long before the vacuum decay timescale is even approached. The threat lives in a future so distant that the word future barely applies, a future on the far side of cosmic death itself. To fear it is a little like a single mayfly, living for one summer afternoon, lying awake worrying about the eventual cooling of the sun. The scales are so mismatched that the worry, however logically real, has no practical meaning at all. So when you hold the timescale honestly, the fear has nowhere to land. The vacuum decay is not coming for you, or your children, or your civilization, or your species, or your world, or your star, or your galaxy, or your era of the cosmos. It waits, if it waits at all, at the very end of everything, past the last light, in a darkness so far away that all of cosmic history as we know it is just a bright flicker at the very beginning of the wait. You can let it rest there, at the end of the longest hallway, and turn back toward the warm and ordinary present, which is the only place you will ever actually be. There is more reassurance too, and it comes from an unexpected place, from nature's own experiments. For billions of years, the universe has been running collisions far more violent than anything we could ever stage. Cosmic rays, particles flung across space at almost the speed of light, have been slamming into each other with energies vastly greater than anything our largest atom smashers can produce, countless times, all over the universe, for the entire history of the cosmos. If those violent collisions could trigger the vacuum to decay, if a high enough energy could nudge the ball over the ridge, then with all those collisions, over all that time, across all that space, it would almost certainly have happened already, somewhere close enough to have reached us. It has not. The universe has been smashing particles together far harder than we ever could for 14 billion years, and the vacuum has held. That is not a proof, but it is a very strong reassurance, written into the simple fact of our continued existence. This is not a closed question, and the story of it is still being written. So it is worth knowing how we might actually sharpen the answer in the years ahead. because the picture could genuinely change, and quite possibly in the reassuring direction. The whole conclusion, remember, balances on a couple of precise numbers: the mass of the Higgs, and especially the mass of the top quark, and on how well we understand the equations that turn those numbers into a verdict about stability. All three of those things can be improved. Physicists are working to measure the top quark mass more precisely, wrestling with the subtle difficulties of pinning down so heavy and fleeting a particle. They are refining the theoretical calculations that connect these masses to the shape of the vacuum landscape, pushing them to greater and greater accuracy. And there are proposals for future particle colliders, even grander than the one we have now, machines that could measure these fundamental quantities with a precision that would dramatically narrow the uncertainty. And perhaps finally tell us clearly which side of the line we're on. It is genuinely possible that within a generation or two, as these measurements sharpen, the answer will settle, and it could settle either way. We might find that the numbers, measured precisely, place us firmly in the stable zone, the ball truly at the bottom, the frightening door revealed to have been a shadow all along. Or we might find that we really are metastable, confirmed, though with the same enormous reassuring timescales that make it harmless in practice. Either way, we will know more than we do now, and the fog around the question will clear. This is one of those rare deep questions about the ultimate fate of reality that is not purely philosophical, but actually connected to measurements we can make, numbers we can improve, experiments we can run. We can chip away at it. We are chipping away at it. There is something I find quietly wonderful about that. The fate of the universe, the stability of empty space itself, the deepest question you could possibly ask about whether reality is permanent, turns out to be tied to the mass of a particle we can weigh in a machine, to a calculation we can refine, to experiments we can build. It is not beyond us. It is a question we are actively, patiently answering, a little more each year, with the same careful, collaborative human work that found the Higgs in the first place. The universe handed us a strange and unsettling note about its own stability, and rather than simply fear it, we are reading it, carefully, word by word, learning to understand exactly what it says. So this is, in the end, a living piece of science, not a settled sentence. The current best reading places us on the knife's edge, but that reading is provisional, balanced on measurements that are still improving. And the next decades may well tip it toward the gentlest answer of all. We are not passive in the face of this question, we are answering it. And whatever the answer turns out to be, it will not change the only thing that matters tonight, which is that the universe is stable now, has been stable for 14 billion years, and will remain stable for so unimaginably long that you, and everyone you love, and everything you will ever know, live entirely inside the safe, steady, settled present, with the frightening door, if it exists at all, locked away at the far end of eternity. I keep returning to cosmic rays, and I want to spend a little while on them properly, because they are, to my mind, the single most reassuring fact in this entire subject, and they deserve to be understood, not just mentioned. A cosmic ray is a particle, usually the nucleus of an atom, flung through space at almost the speed of light by some violent event, an exploding star, a feeding black hole, some cosmic engine of tremendous power. These particles fill the universe. They are streaming through the room you're in right now, passing through your body, harmless and constant. And some of them carry truly staggering energies, far, far more than anything human beings can produce. Our largest particle collider, that 17-mile ring beneath Europe, is a marvel. But the most energetic cosmic rays carry millions of times more energy than the particles it accelerates. Nature, in other words, runs experiments that dwarf our greatest machines, all the time, everywhere, for free. And these high-energy particles collide. They slam into the atmosphere of the Earth, into the surfaces of planets and stars, into each other in the thin gas between the stars countless times across the whole universe for the entire 14 billion years it has existed. Every one of those collisions is a little experiment, a tiny region where energy is concentrated to a degree that, if anything could trigger the vacuum to decay, might do it. If there was some energy threshold, some violent enough event that could nudge the false vacuum over the ridge, then in all those collisions, over all that time, across all that vast space, it would almost certainly have been crossed somewhere, at some point, close enough to us that the resulting bubble would have reached us by now. It has not. The vacuum has held through every one of those collisions, every cosmic ray, every violent event in the entire history and breadth of the universe. That is an experiment of incomprehensible scale, run continuously since the beginning of time. And the answer it has returned every single time is that the vacuum does not decay, not at any energy nature has managed to reach, not anywhere we could have felt. Our own continued existence is the result of that experiment, written across 14 billion years. This is why physicists are genuinely unworried about anything we might do. The fear that a human experiment could end the universe runs straight into this wall of evidence. We cannot come close to the energies that cosmic rays reach as a matter of routine. And those energies, applied countless times across the cosmos, have never triggered anything. To worry that our little machines could do what the universe's most violent events have failed to do for billions of years is to misunderstand the scales involved by an almost unimaginable margin. We are not playing with fire. We are striking matches in a universe that has been setting off bombs since before the Earth existed. And the vacuum has not so much as flickered. So when the frightening thought creeps in that the end could come at any moment, set it beside this. For 14 billion years, the universe has been doing everything in its power to trigger that end, throwing the most violent collisions it can produce at the vacuum, over and over, everywhere at once. And the vacuum has simply held calm and steady through all of it. That is not a guarantee. Nothing in physics is an absolute guarantee, but it is about as close to reassurance as the universe can offer. And it is written into the simple, miraculous fact that you are here, in a calm room, on a quiet night, with a sky full of undisturbed stars. By the end of tonight, here is what I hope sits with you, instead of fear. The vacuum decay idea is real physics, a genuine possibility that serious people study with great care. It tells us something profound and humbling about the deep structure of reality, that even empty space, the most settled thing there is, may have hidden depths, may be balanced on an edge we cannot see. That is a wondrous thing to know, but it is not a thing to fear, because the very same physics that makes it possible also makes it, for any timescale that could ever touch a life, almost infinitely unlikely. You're safe. You have always been safe. The universe has held for 14 billion years, and it will almost certainly hold for countless billions more, far longer than the stars themselves. The frightening door is real. But it is locked with a key made of numbers so large that no living thing will ever see it open. When this idea first reached the wider world, in the years after the Higgs was found, it arrived, predictably, dressed in the most dramatic language possible. And one of the most famous scientists who ever lived was briefly at the centre of it. It is worth telling that story because it is a small lesson in how a careful scientific idea turns into a frightening headline, and how to read past the fear to the calm underneath. Around 2014, Stephen Hawking, writing in the preface to a book, mentioned this very possibility that the Higgs field could, under certain conditions, become unstable and trigger a catastrophic decay of the vacuum. The press did exactly what you would expect. Headlines bloomed about Hawking warning that the Higgs boson could destroy the universe, that the famous physicist had predicted doomsday, that the end was somehow nigh. It was, for a brief moment, a small global scare, the kind of thing that gets shared and reshared with alarming punctuation. But look at what Hawking actually said, because it is a perfect example of the gap between the science and the scare. He noted that the vacuum could become unstable, yes, but only at energies so enormous that triggering it deliberately would require a particle collider larger than the entire Earth, bigger even than the solar system. And he was clear, as anyone who understood the physics was clear, that this was not something that would happen on any timescale that could possibly matter, not in our lifetimes, not in anything resembling the foreseeable future of the universe. The frightening part made the headlines. The reassuring part, which was most of what he actually said, did not. The science was calm, the coverage was not. This is worth remembering whenever you encounter this idea in the wild, because you will, and it will almost always be dressed in fear. The pattern is always the same. A real, careful, deeply hedged piece of physics, full of qualifications and enormous timescales and honest uncertainty, gets compressed into a headline that keeps only the scary part and throws away all the context that makes it harmless. The vacuum could decay becomes the universe might end at any second. The technically true becomes the emotionally terrifying by the simple act of leaving out the numbers that make it safe. And millions of people feel a small chill, for no good reason, because the reassurance was the part that did not fit in the headline. So let this be a kind of inoculation. You now know more about this subject than almost anyone who's ever been frightened by a headline about it. You know that it is a real possibility, but a deeply uncertain one. You know that the timescales involved stretch past the death of the stars. You know that nature has been trying and failing to trigger it for 14 billion years. You know that even the great Hawking, when you actually read his words rather than the headlines about them, was describing something safely locked away behind energies and timescales beyond all meaning. The fear is in the telling. The physics, properly understood, is calm. And there is something freeing in that, in being able to meet one of these alarming headlines the next time you see one, with a quiet inner steadiness rather than a flinch. You can read the scary words and understand the careful science underneath them, and feel, instead of dread, a kind of fond recognition. Ah, you can think, this one again. The universe is still here. It has been here for 14 billion years, and it will almost certainly be here, steady and humming and stable, long after every headline ever written has been forgotten. Let us set the physics down for a few minutes and sit with the feeling of all this. Because underneath the equations there is something genuinely human here, something worth turning over gently in the dark. The idea that the universe might not be permanent, that even empty space might be provisional, balanced on an edge, touches something old in us. We want the ground to be solid. We want at least the largest things, the sky, the stars, the universe itself, to be the one set of things we can count on absolutely. The backdrop that does not move while everything in the foreground comes and goes. And there is a small vertigo in learning that even the backdrop may be temporary, that the stage itself may be the kind of thing that could someday change. It can feel, for a moment, like there is nothing left to hold on to, if even the universe is impermanent. But here is the gentler way to hold it, and I think it is also the truer way. Everything you have ever loved has been impermanent, and that has never made it less worth loving. A sunset is impermanent. A song is impermanent. A single, perfect, ordinary day is impermanent. The people we love are impermanent, and so are we. And yet impermanence does not empty any of it of meaning. If anything, it is part of what gives these things their meaning, their preciousness, their weight. A thing does not have to last forever to matter. It only has to be here, now, and real. The universe being impermanent on some unimaginable timescale does not make it less astonishing that it is here at all, that you are here at all, that any of this brief, bright, improbable existence is happening. And notice the proportion. The impermanence of the universe, if it is even real, plays out over timescales so vast that they are for any purpose that could ever touch you, indistinguishable from forever. The impermanence that actually shapes a human life, the impermanence of a day, a season, a lifetime, is real and near and woven into everything. The impermanence of the universe is so distant that it's almost a kind of abstraction, a fact about eternity rather than a fact about your life. To trade the warmth of the present for anxiety about the fate of the vacuum, ages past the death of the stars, would be to let the most remote possible thing steal something from the most immediate real thing, which is this night, this breath, this quiet, this rest. There is a long tradition, in many of the ways humans have tried to be wise, of finding peace precisely by accepting impermanence rather than fighting it. The thought that nothing lasts forever, fully accepted, does not have to be a source of dread. It can be a source of presence, of gratitude, of a deeper attention to what is here while it is here. The universe may not be permanent, neither are you. And in the meantime, there is this, the extraordinary fact of being here at all, in a cosmos stable enough and patient enough to have made you, on a night quiet enough to think these thoughts. That is not diminished by the distant possibility of an ending. It is, if anything, made more precious by it. So let the impermanence be, if it is even real. It changes nothing about the worth of this moment, and it asks nothing of you tonight but to notice gently how remarkable it is to be here, now, in a universe that has held itself steady long enough for you to rest inside it. That steadiness is the only relationship with the universe you will ever actually have. The far-off ending, real or not, belongs to a future so distant it is almost a different kind of thing. This night belongs to you. So where does all of this leave us lying here in the quiet at the end of a long day? We started with a number, the mass of the Higgs boson, and the strange message it seemed to carry, that empty space, the most stable thing we can imagine, might not be truly at the bottom. We learned what a false vacuum is, a valley that only looks like the lowest point, with a deeper valley hidden somewhere beyond the ridge. We found that our universe seems to sit almost exactly on the knife's edge between stability and collapse, balanced, metastable, neither clearly safe forever nor clearly doomed. We opened the third door, the one with no timeline, and looked at what waits behind it. A bubble of true vacuum, appearing from nowhere by pure quantum chance, spreading outward at the speed of light, giving no warning. Because the warning and the ending travel at the very same speed. We sat with the vertiginous thought in the title that somewhere out there, the end may already have begun, and may be racing toward us through the dark, hidden inside its own silence, and that we could never know. And then we walked out the other side, into the reassurance, which is just as real. The universe has held for nearly 14 billion years. Nature has been smashing particles together far harder than we ever could, all that time, all across space, and the vacuum has not fallen. And the numbers say that if it ever does decay, the wait would be so unimaginably long that the stars would all burn out first, that the universe would grow cold and dark and empty ages before the third door ever opened. The danger is real in principle, and almost infinitely unlikely in practice, locked away behind numbers so vast they fold back around into something that feels like peace. Here is the thought I want to leave you with, and it is a gentle one. The possibility that the universe has already ended somewhere, that the end is silently on its way, sounds like the most frightening idea imaginable. But turn it over and look at the other side. It means that right now, this moment, the one you are in, is not promised, was never promised, and is therefore a kind of quiet gift. Every ordinary night, including this one, is a night the universe held together. The vacuum stayed in its valley. The stars kept shining. And you got to lie here, warm and safe, thinking strange and beautiful thoughts about the deep nature of reality. That is not something to fear. That is something to be quietly grateful for. The universe did not have to be this stable, And yet, every night so far, it has been. So let the frightening part go now. You walked all the way through it, and out the other side, and the other side is calm. The vacuum is holding, as it has held for 14 billion years. The deeper valley, if it is even there, is unimaginably far from being reached, far beyond the lifetime of the stars, far beyond anything that could ever touch you or anyone you love. The sky outside is exactly as calm as it looks. There is no wall racing toward you through the dark, and even if, in some vanishingly unlikely corner of possibility there were, it would ask nothing of you, no fear, no dread, nothing but the rest you're already settling into. Empty space is holding you, steady and quiet and stable, the way it has held everything, always. Let it. There is nothing to watch for. There is nothing coming. There is only this ordinary, miraculous, perfectly stable night, and you, safe inside it, free to close your eyes, sleep well,